So what we ended with yesterday is we talked about unit vectors. We talked about if you take a vector and you divide by the magnitude, you're going to get a unit vector, and that process is called normalizing. So we're going to do another example real quick before we talk about another form of vectors. We are going to find the unit vector. In the direction we're going to call our vector A. That vector is going to be 2i subtract j subtract 2k. So I want a vector that is in the same direction, but that has a magnitude of 1. That'll make it a unit vector. So how are we going to start? Find the magnitude. Yeah. So this is what we did yesterday. You're going to take the square root. You're going to square each of the coefficients. So we end up with a magnitude of 3. So then what you're going to do is you're going to divide your vector by 3 so that we have a length of 1. So I'm going to call this a sub u so that it's a unit vector. That's one way that you can write it. Other way is in bracket notation. So that would be our unit vector that's in the same direction. Sound good? Okay. Great. Oftentimes we want to write a vector in terms of a direction, which is going to be a unit vector, and a length. So that's what we're going to talk about next, is when we have vectors that are determined by a length and angle. Here's that form. I can write a vector as the product of its length and then the angle that it makes with the x-axis. That'll be the vector cosine theta, comma sine theta. This is obviously the length. This part we call the direction of the vector. So oftentimes you'll be asked to write a vector in terms of its magnitude and its direction. Okay, example 5. We are going to find the angle. That vector v. V is going to be the vector negative root 3 comma 1. We are going to find the angle that that vector makes with the positive x-axis. Okay, one method that has nothing to do with this formula is to draw a picture. So you can draw a picture, you can draw on the triangle. Does that make sense without me drawing it? Okay, we're going to do this instead though. So we are going to take that vector v, so that negative root 3 comma 1, and we want to write that as the product of its magnitude multiplied by its direction. So theta ultimately is what we're looking for. If you find the magnitude, you're going to find that it's 2. So once we divide by 2, we're going to get our direction vector. So this tells us 2 pieces of information. It tells us that cosine of theta is negative root 3 over 2, and that sine of theta is 1/2. Therefore, what is theta? 5 pi over 6. Yesterday, one of you asked me if you should be using calculators on your homework. I don't have a preference either way, but I will tell you, whenever possible on your exam, you will not be permitted a calculator. So your final, for sure, you will not be permitted a calculator. And most chapters, you won't be permitted a calculator on the exam. So you need to make sure that you have the unit circle memorized and that you feel comfortable taking most of your exams without a calculator. Like I said, homework, I don't care. If you want to use a calculator, go for it. But just make sure you're comfortable doing that. Any questions on that form of a vector? Using length and magnitude, or length and angle, rather. Okay, last thing we need to talk about is applications. Okay, so we talked about yesterday with vectors, we have some common uses of vectors that we're going to use throughout the semester. One that I said is force. So today we're going to be talking about forces. Forces are often represented by vectors because they have a length and a direction. What we're going to be talking about today is when you have two or more forces applied to the same point. So if two forces are applied to the same point, do you guys know what that's called if two forces are applied to the same point? Starts with a C. Okay, I'll tell you. They're called concurrent. Is that a term that you've heard in physics or anything? Yeah, so concurrent forces applied to the same point. What we are interested in is the resultant force. So the two forces together form the resultant force. The resultant force is going to be the sum of the two forces applied to the same point. So we are going to do 2 examples, and then that's the end of notes for this section. Okay. Okay, suppose that 2 forces are applied to an I bracket. Find the magnitude of the resultant. And the angle it makes with the positive x-axis. And then that's the resulting figure. This is what we're talking about. Yes, 30 and 40. Okay, so we wrote previously that the resultant force, I'm just going to call it big F, is going to be the sum of the 2 concurrent forces. So first thing we need is we need the 2 forces in a more helpful form, like maybe bracket notation. So that F1, the first force, we know the magnitude is 200. And we know that we have an angle of 30. So we can write it in terms of its magnitude and its direction. So this will be 200 cosine of 30, comma sine of 30. So that first force then, cosine of 30, anyone? Square root of 3 over 2. So this will be 100 root 3, comma 100. Second force we're going to write in the same manner. Magnitude is 300. This time we have cosine of 70, sine of 70. Please do not round until the very end. So we're just going to leave this as 300 cosine of 70, comma 300 sine of 70. So then,
so let's say F2.
Yes. So then our resultant force is going to happen when we add our two forces together. So right now we're going to add these two together to get the resultant. So this will be 100 root 3, add 300 cosine of 70, and then 100 add 300 sine of 70. This is about 275.8, comma 381.9. Okay, now that we have the resultant force, we are asked for the magnitude and the angle it makes with the positive x-axis. Are you all comfortable finding magnitude from here? Can I just tell you what it ends up being? Okay, the magnitude of the resultant ends up being about 471. Okay. So what we can do then is we know that the cosine of theta is going to be this number divided by the magnitude. Please don't use the rounded value though, use that 100 root 3 plus 300 cosine of 70. We could also do sine, I just chose cosine. That theta is going to end up being 54.2 degrees. Questions? Okay, I don't know if WebAssign uses radians or degrees, so please make sure that you just pay attention and give the answer however it's asked. Okay, last example. A 100-pound weight hangs from two wires. Find the forces, could be referred to as the tensions. So I'm going to call them T1 and T2 in both wires, and the magnitude of those tensions. this is what we're looking at. So we have this wire here holding up that 100-pound weight. I'm going to call this W for the weight. So the first thing we know is that these two wires are going to result in holding the weight up. So we know that that vector T1, when we add the vector T2, we're going to get the vector W. Because we have the weight balanced. Vector W should be the easiest one to write. Anyone? 0, negative 100. Okay, so then let's write this T1 and T2 then. So T1 is going to be the magnitude of T1, of the tension, and then cosine of something, sine of something. This is T1. If this is 50 degrees, this is 50 degrees. 50 degrees is not the angle that we want to use, though. What angle do you want to use? 180 minus 82. 180 minus 82? You guys agree? Measuring from the positive x-axis. Yeah, 180 minus 50, right? This angle here, measuring from the positive x-axis. So this is going to be 130. It might be helpful to write this in terms of 50 instead. So that's what we're going to do. How does cosine of 130 relate to cosine of 50? Yeah, same value, opposite sign. So this is the same as writing negative cosine of 50. How does sine of 130 relate to sine of 50? They're the same. Are you all with me? Yeah, we're good? Okay, so let's write our second tension then. This one is a little bit easier. We can just use 32. 32 is already the measurement from the positive x-axis. Okay, and what we said is if I take that first tension and I add that second tension, I should get the vector for the weight, which is 0, negative 100. Okay. So what I'm going to do is I'm going to add the x components, I'm going to add the y components. So I add this one, add this one. So I get negative norm of T1 cosine of 50 plus norm of T2 cosine of 32. That's all the x component. Do the same one for y. Ran out of room, sorry. Okay, ideas for solving this. What do we have? What is this? It's a system. Yeah, it gives us two pieces of information. We have the x-coordinate, we have the y-coordinate. I'm just going to call this from now on T1, and I'm going to call this from now on T2, so I don't have to keep writing the magnitude sign. So we get negative T1 cosine of 50 plus T2 cosine of 32 equals 0. Likewise, we have T1 sine of 50 plus T2 sine of 32 equals 100. I'm going to do substitution, starting with that first equation. First equation tells us that T1 cosine of 50 is equal to T2 cosine of 32. T2 then is T1 times cosine of 50 over cosine of 32. If I go to that second equation then, I have T1 sine of 50 plus, instead of T2, we're going to use the expression we just came up with. So that's T1 cosine of 50 over cosine of 32 times sine of 32 equals 100.
Should we keep it at negative 100?
Yes, thank you. That's a negative. Oh. No, it is supposed to be positive. Okay. If we go back up here, sorry, I misspoke on this. W is in fact 0, negative 100. Now what we need is we need the resultant of these two wires to balance this, to counteract it, right? So that the weight doesn't move. So these actually end up being, when you add them together, are going to be the opposite of the wire to keep it balanced. So this should be a positive 100. Sorry about that. Does that make sense? We want to balance the weight, we don't want it to move. So that's why they're going to end up being the opposite. Thank you for catching that. Okay, so if we solve for T1 then, T1 is going to be 100. If I factor out the T1, I'm going to end up with sine of 50 plus cosine of 50 times the tangent of 32. Remember that I got lazy though, that T1 really represents the magnitude of the first tension vector. That ends up being about 85.64 pounds. If you plug that back in up here, you'll get the magnitude of the second tension vector. That ends up being about 64.91. Question asks us to find the tensions and find the magnitudes. So right now we found the magnitudes. I want you to find the vectors. Are you all comfortable with that? Going back, plugging this in to there or there. Plugging that in right there. Yeah? Are you okay if I just tell you what it ends up being? Okay, first tension vector ends up being about negative 55.05, comma 65.6. Second tension vector ends up being 55.05, comma 34.4. Do we have any questions on all things vectors?
So first, you found the magnitude for T1.
Mm-hmm.
And to find T1 vector,
Yep.
what did you do?
Went back to the way we defined it initially up here.
And then did you multiply that by cosine 130?
Uh-huh. Yep. Anything else? On applications or anything else vectors?